Okay, so I gave you quite a few bits of observational data yesterday, evidence for all sorts of things in the universe. So what I want to do is just step through some of the things I said yesterday. I've had a few questions along the way, but I'm hoping to get a few questions right now. Those lights off. All right, so it looks like you'll need a bit of time to think. Here are a few. I'm likely to need a bit of time to think of some of these. Okay. All right. So, I think what I'll do is I'll step through some of the things, and then I'll come back to your questions a little later. Okay, and I might answer some of them as we go. I'm still waiting for some from the NASP students up there. Any old question, you know. Okay, so I wanted to go as far as that. Okay, so we're talking about evidence for the Big Bang, and we said that when we looked out, we saw that galaxies were moving away from us. Okay, and that meant either we could assume that we're at the center of the universe and everything was just moving away from us, or you could come up with a much more plausible explanation, and that is that the space between the galaxies was expanding. And someone asked me a question yesterday. You know, we used to, in cosmology talks, people used to talk a lot about the cosmological principle, which says that we're not at the center of the universe. We're not important, okay? So I just took that for granted. I spent enough time looking at the universe to convince myself that we're not at the center of the universe. And we have this really nice plausible explanation with the space expanding, plus we have all of this other evidence that I've been giving. So I think it's a really good thing to start with to say that we're not at the center of the universe. So we would have galaxies that are moving away from us, and that is because the space is expanding. Okay. Then there's the cosmic microwave background. So we said that if we looked out into space, okay, remember I showed you that sort of diagram where you were over here, and you look out, and of course a galaxy out here, the light's taken some time to reach you. Okay, so you see that galaxy as it was a long time ago. Then this galaxy, the light's taken even longer to reach you, so you see it even a longer time ago. And eventually you get to a region of space where you're looking so far out that you're seeing the universe as it was very early on. Okay? So we see light coming to us from that time when the universe was really, really young. Okay? And so we said that it was opaque and photons couldn't travel very far without bumping into something. So then as the space expanded, so the light could escape, and it travels all the way through space to reach us down here. And of course it does encounter some things along the way, but we have this very, very homogeneous black body spectrum of light coming to us from early times. Okay? So I'm going to talk quite a lot more about the cosmic microwave background. It would be good to clear up any problems with that now. Okay? So I'll ask someone to say, okay, this is a question I get. If I wanted to go and look for the microwave background, which direction should I look? Where should I look in the sky? What constellation or something? How would you answer a question like that? Yeah. Everywhere. Of course, because we're looking out, okay, over here. We look everywhere, and wherever we look, we eventually look far enough back in time to see light coming to us from the cosmic microwave background. Okay, so that was another piece of evidence for the Big Bang. And we talked about Big Bang nucleosynthesis. Okay, if we look out into space, we see that about a quarter of the baryons are in helium, and we can't possibly have made that all in the stars. And it's very consistent with there having been a period in the universe's history when it was much hotter and denser, so the whole universe was like the inside of a star, and we were burning hydrogen to helium through fusion. Sorry, sometimes there's confusion about that when astronomers talk about burning. Of course, they don't mean anything to do with oxygen. They mean nuclear fusion of hydrogen to make helium. Okay? And I showed you this little diagram where we could make predictions of the amounts of different types of elements produced in the early universe, and the amounts that we predict were very, very sensitive to the baryonic density early on. Okay, so I'll get back to that in a second. All right. Then we were talking about the contents of the universe, and I had this maybe a little strange way of saying what's in the universe. We talked about the baryons. Okay, then there's this, and we said that there was dark matter, but at first we didn't say the dark matter was needed to be anything different from baryons. But then I showed you with the Big Bang nucleosynthesis constraints that dark matter really needs to be something other than baryons. And then I very briefly mentioned the dark energy or the cosmological constant. We've got another whole talk on that and more talks next week. So I'm not going to talk that much more. I'm going to talk about the CMB, so you'll see some more of that. Okay, and then I said that usually the amounts of these kinds of stuff are expressed in terms of the critical density. Okay, so the critical density is the density that's required for the universe just to start expanding and then slowly drift down to zero expansion. Okay, and so obviously we can just label those baryonic matter and lambda contributions. And I said that if it was a closed universe, so we had a lot of matter, it would expand and then contract. And if we had critical density, it would just drift. And an open universe would carry on expanding, but not too fast. Now, if you put some cosmological constant type stuff in there, then you're going to get an increase in the expansion rate. So you recognize the sort of basic Friedmann equation from some factor of kc squared. So this is if we just say that the universe is flat for now. So just put k equal to 0 for now, and you look at this. So we've got a density in here. Okay, this is the scale factor, so it's kind of the average distance between galaxies and how fast that's changing. All right. So we've got a density that depends on the density of the stuff in it. So we can think of rho matter, for example. How is that going to evolve with a scale factor? If you've just got some matter and you increase your volume of space by you increase the volume by 2, what's going to happen? Well, the density is going to go down as 1 over r cubed, right? So something like cosmological constant density will go as a constant. Okay? So when at later times you're going to get this factor in here with an r squared. So the change in r is going to be going as r squared. So the universe is going to be expanding, and it's going to be an increasing expansion rate. Okay, so that's the kind of stuff in the universe. I had a question here about the acceleration of space, the acceleration of the expansion, and someone said, "Well, what happens when the space is expanding at the same as the speed of light? Okay, isn't that going to be a problem?" And no, that's not a problem. The thing that we can't have is galaxies traveling through the space faster than the speed of light. Okay? That's what we can't have. So when you look back and you see that a galaxy appears to be moving away from you at faster than the speed of light, that's because the space is expanding quickly. Okay? Well, close. All right, so we talked about evidence for dark matter. Does someone just want to explain what was on this diagram here? What were we talking about here? So what's plotted along here? Distance from the center of the galaxy, yeah?
You would expect the velocity of planets far further out to decrease more steeply if all the mass were centered at the center of the galaxy.
Exactly.
The fact that velocity doesn't decrease means there's mass elsewhere.
Right, so we look at gas clouds, actually not planets, but gas clouds, well beyond where the stars are. Okay, so we look out here, we look at sort of neutral hydrogen with a radio telescope or something, look out there, and I don't know can you actually see from there if I draw on the board, yeah? So if I've got a galaxy and I'm looking edge on, and I rub the rest of the universe off next to it, okay, and I go and measure velocities of gas clouds way out from the stars here, okay, if all the mass were inward towards the center of the galaxy, you would expect, okay, I'm going to plot the distance from the center. Sorry, I'm going backwards. Let me make A, B, and C over here. A, B, and C on the distance side there. Then you would expect that the rotation, the speed of these things would increase, and then when you got far out from the center, it would decrease again. That's what you would expect. But actually, you find that A, B, and C are out there, and we conclude that there's a lot of mass beyond where the stars are. Okay? Problems with that? All right. The other evidence for dark matter was these distortions of background galaxies by the foreground cluster. Okay? I had a question that was sort of asking, well, what were these things? So in this picture, this is actually most of these are a single galaxy, which are very closely aligned with us, then the cluster, then the background galaxy. Okay, and it's almost spread out into that Einstein ring that I showed you. Okay, so it's very close to being aligned. And then beyond that, these other galaxies here would be also a little distorted by the foreground. And from those distortions, you can infer the amount of mass, and we have lots of mass in the cluster. Okay, there was the evidence that the dark matter is not baryonic. And some evidence for dark energy. Okay, and that was where we got to yesterday, the summary of the main ideas. Any questions about that? Let's just see if I've got anything else here. Well, while you're thinking, I'll answer this question here, which says, how does quasars fit in with galaxies? Because a lot of the lensing pictures I showed you, we had some kind of lens here, so either a galaxy or a cluster of galaxies, and beyond it was a quasar. So what's a quasar? That is just the very central region of a galaxy. And it's incredibly bright because we believe that you have a supermassive black hole there, and you have a lot of stuff falling in onto an accretion disk around the black hole, and so it loses all of its energy and it emits a lot of light. There's a lot of energy, emits a lot of light, so it looks very bright. Okay, so the center of a galaxy can look very, very bright if you have this kind of active region at the center where the supermassive black hole is. So that's a quasar, and you often just see the central region. When I talked about a hot Big Bang, what kind of temperatures are we looking at? Infinite. Does that mean the temperature has no upper bound? Well, we can run it backwards and backwards and backwards in time, and it gets hotter and hotter and hotter, and then we can say less and less and less about what's going on. Okay? So you can, I would always just think about the region of, got some more questions up there. Sorry, let me just take the questions. So I don't want to say anything about, at least, well, we can say we know things about up to Big Bang nucleosynthesis time, so that's 1 second after the Big Bang. And before that, the particle physicists will tell you more about what's happening, and you can go even further, and maybe the string theorists can tell you something. And all I know is it's getting hotter and hotter, and that's I think, all we can really say. what happens at t equals 0. Okay, I think I'm going to leave that for now, but I can come back to it, okay, which is just talking more about what is the dark matter. All right, we sort of thought a bit about it, said maybe little black holes, maybe a sea of weakly interacting massive particles, something like that. But I can come back to that because that's a sort of tutorial problem on lensing. What we do is we use lensing to try and find out if there are little black holes as dark matter around galaxies. Okay, but first let me talk about the CMB because this is really very exciting. What I show here is the whole sky. So the way you should picture that is take that ellipse, wrap it around your head. Okay, this is up above you. That's down below you. Okay? So this is a very generic picture you see everywhere. So now you know this is the whole sky. Just wrap it around your head. Okay? So if we look at around the temperature of the photons coming at us from distant times, they look like they're at 3 Kelvin. Now, of course, they've been redshifted. Okay, so it was much hotter, around 3,000 Kelvin when they first set out towards us. Then what's this? Well, if you look at about the 10 to the minus 3 level, look for fluctuations in the temperature of the CMB at the 10 to the minus 3 level. So let me just do very roughly what I mean by that. So we have a black body. These are pictures taken at, I don't know, maybe 53 gigahertz or something. So you look in one region of the sky and you measure a brightness there, and then you look at another region and maybe you measure a brightness there and a brightness there, and you match that onto the black body. Okay, so the region here, you'll associate a slightly hotter temperature. The region there, you'll associate a slightly cooler temperature. So what does this mean? The 10 to the minus 3 level, you look out and there's one like hot patch and one cool patch, 180 degrees separated. Weird universe. Any ideas? Right, there we go. So the Earth is moving with respect to the background. Okay, the Earth's going around the sun's going around the galaxy's traveling through space, and we can measure that motion with respect to the cosmic microwave background. So as we move towards the cosmic microwave background over here, the things look like they're coming faster. They're slightly blue shifted. From here, they're slightly red shifted. So you have these hot and cold spots. Okay, that's the 10 to the minus 3 level. So we're looking at something that's like 2.7 Kelvin. Now we're at 10 to the minus 3 of that. You look down 10 to the minus 5. Okay, so we're looking at really tiny fluctuations in the cosmic microwave background. All right? So you got a 100-meter lake. You're looking at a little ripple this size. Okay, and you see this. So what's that? Weird universe. Okay, this is wrapped around your head. So all the way around like this, there's some band of emission. A galaxy, right, our own galaxy. Because we're sitting in a disk, right? So when you look out and you see a band of the Milky Way, okay, that's emitting a little bit of light at that. Right? So that's not so interesting for people doing fundamental physics, but this part certainly is. Those are fluctuations in the CMB that correspond to real density fluctuations at very early times. Okay? All right, so now we said we had some dark matter and we had some dark energy. So now the CMB can provide a nice way of constraining this. Okay, so I've said that fluctuations in the temperature of the CMB provide a direct probe of the density fluctuations. Okay, so this is, I don't know if this will help you. This is present over here. We're looking back in time over there. That was the inflation that Roy Martins talked about, the time when we have the rapid expansion. Okay, the universe is still opaque in this region, and here the photons decouple and start traveling through the space without uninterrupted. Okay. So, if you go and do not fundamental physics, just ordinary old boring physics, you expect that you could get these acoustic oscillations occurring on scales that are within causal contact. Okay, so that's important. At early times, there's a certain size of space which has had time to communicate. Right? So in that region, you can get acoustic oscillations set up. All right, so that gives us a length scale at early times. That's very important. Okay. So the physical scale of fundamental mode can be calculated, boring physics. Fluctuations in temperature are particularly pronounced on the scale. Okay, so if we look at the cosmic microwave background, we see quite big fluctuations in temperature on that scale. Okay, and at scales corresponding to harmonics. Okay, and the geometry of space can be determined by comparing the calculated physical scale with the observed scale. Okay, slightly oversimplified, but there you go. So what have I got plotted here? Along here is angular scale. Okay, with large scales on this side, small scales on this side. Okay? Large scales, small scales. And these are the sort of size of the fluctuations you see on those angular scales. So, for example, here on large scales, we see not so much fluctuation. And suddenly, just around there, you see lots of fluctuation. Okay? And that corresponds to those acoustic oscillations. So that angular scale is where you have the sort of fundamental mode. So that gives you the region of causal contact at early times. Okay? Just like sound waves. So, yes, for the baryon-photon combination. So the amount of the amount of baryons has an effect on how big the oscillations are. Okay. I'll say that in a second. Just going back to this, so this would be fluctuations on very large scales, right? So what can we say about what's been done to that fluctuation? It's been taken out of this, right? Otherwise, we'd have a huge fluctuation here on those large scales.
Just a quick question. The graph you're plotting there, does that come from experimental data? It's not from any...
Indeed. Very, very impressive. Looking at 10 to the minus 5 level on scales 2 degrees, 0.2 degrees. Okay. So if I just go back to this picture, this is probably, I don't know, what is it, 10 degrees or more? Okay, and then you look on smaller and smaller fluctuation scales. And so these are measurements from the WMAP satellite. So that the results came out last year. These, not all the points. There's a collection from a few different experiments. Some of them are on the ground. You can see there's like interferometers do the small scales. I'm not going to go into it that much, but so a lot of it is data from the WMAP satellite experiment. So just think about those peaks there. I mean, like if I asked you, what are those two things? We've said that this is the scale on which you get the kind of fundamental mode. So those would be the sort of harmonics, right? You've got this baryon photon fluid kind of oscillating around. Okay, but the title of that was Constraining Dark Energy. I haven't said anything about dark energy yet, but let's just keep going here. All right, so there's that same picture that you saw. And if you just think about the geometry of space, okay, so we could think about a flat space where we've said that we basically have a length scale at early times, which was the sort of distance for causal contact at the CMB time. So we have a length scale, like a ruler. Someone asked me yesterday if we can just do pure geometry to measure cosmological parameters, and that's pretty much what this is. Okay, we have a length scale, and we sort of measure the angle that we see for that length scale. Okay, so you can imagine in a flat space, it has a certain angular scale. Okay, if it's curved space, curved like that, so then now you've got your smaller angular scale, but it's being bent into your line of sight like this. Okay, so it kind of looks bigger to us. So then that peak would shift to larger angular scales if the space were curved. So the position of this peak tells us about the geometry. Okay? And if the space were curved, we would shift this peak because of just how you see the angular scale in a curved space or a flat space. So this little thing down here is just showing you how that peak would shift as you increase increasing the curvature. Okay, so we're actually making it more and more open. That's a closed space, we're making more and more open, so we're shifting the peak in the opposite direction. Okay. So you should just take away that the position of that peak tells us about the geometry. All right, so yesterday I showed you the supernova results, where we had plotted the constraints on omega lambda and omega matter from supernova. Okay, so measuring the brightnesses of supernova, and we said that the allowable region was here, okay, implying a non-zero cosmological constant or non-zero contribution from cosmological constant type stuff. And the CMB data constrain you in that green region. Yeah, there's actually, you can't really see it. It goes all the way down here. And the dark region there is the more likely region, which matches very well with the supernova results. Okay, so we've got two sets of results which seem to constrain omega matter and omega lambda. Okay, so this is the density of matter. Okay, is around 0.3 times the critical density, which is just a number. Okay, so that's just a density. And omega lambda of around 0.7. Okay, so that's consistent with the supernova results and the CMB results. All right. And what you can do is you can go and look at large-scale structure as well. And what you do is you look at the evolution of clustering of galaxies over time, and that also depends on the cosmological parameters. Okay, so looking at the evolution of clustering over time, and that puts in another constraint on these things, which matches nicely. So even if you dream up scenarios where your supernova have different brightnesses at large distances, and you want to check out those supernova results altogether, you still have to deal with the large-scale structure observations, which, as you can see, are quite constraining there. Okay. So do you just want to... How do you get this constraint again? Let me remind you, is that the evolution of clustering of galaxies depends on these cosmological parameters. Okay, so we're still dealing with these cosmic microwave background fluctuations. Here's that familiar plot now. And all this is showing is what happens when you change the density of baryons. Okay. And what I said was we set up these oscillations. So the first one is a compression peak. The second one, a rarefaction peak. The third one is a compression peak. So these are when the fluid is compressing. This is when it's rarefying. Okay, so if you increase the amount of baryons, it's the sort of gravity of the baryons holds that compression peak more. So the rarefaction peak decreases relative to the compression peaks. And that's what you see here. If it went a little slower, you can see that middle peak disappearing there. Okay. So the heights of those peaks give you a constraint on omega baryon as well. All right. So we had that one piece of evidence, the Big Bang nucleosynthesis, which constrained omega baryon, but now we've got this other piece as well. There are two pieces of evidence. Okay, questions about?
I ask you, what it constrains a megabaryon to be? By looking at the relative sizes of the tail
You usually quote it in terms of omega b times the Hubble constant squared. So I'm not sure that the number would mean that much to you. But it is consistent with Big Bang nucleosynthesis just. So it's about 4% of total. Yeah, it's a powerful hand. But so is Big Bang nucleosynthesis, right? So they both provide constraints on the amount of baryons. It's about 4%. Okay. Any questions on the CMB? All right, so now we want to start thinking about what this stuff might be. This dark matter, dark energy. We've got only 4% of the stuff we know anything about. It's kind of alarming. So you can start thinking dark matter could be hot or cold, right? So what do I mean by hot or cold? I mean non-relativistic at the time of decoupling, okay? And why is that important? Well, when you produce your dark matter, you're going to have density fluctuations which are eventually going to collapse, okay, to form your galaxies and everything you see today. All right, maybe I should have made that a little clearer yesterday, that the way we build up structure today and through time is through the gravitational collapse of these little density fluctuations early on. Okay? So we can look at the clustering of the galaxies that we see today, and we can say, all right, what kind of fluctuations did we need early on to produce those things? So if all the dark matter were hot, okay, something like a light neutrino, then those initial density fluctuations would be the small scale fluctuations would be washed out, okay, because the neutrinos can travel easily. Okay, so you have these little fluctuations, neutrinos could, the hot dark matter could travel easily and wash out the small scale fluctuations. All right, so if dark matter is hot, then small scale density fluctuations are washed out at early times. Large structures form first. Okay, so that means that the large structures collapse first, and you've got to fragment these things to produce galaxies later on. Yeah.
I'm not entirely sure what you mean by non-relativistic. What alternatives are there?
It's just how fast the thing's moving, really.
Oh, okay. So relativity still applies. It's just not fast enough for relativity to be relevant.
Right. Exactly. Yeah. Yeah. So if it's light, it will go fast and wash out the structure. Okay. So if dark matter is cold, then the small structures form first. So we get the little density fluctuations remain. They collapse to form like little small galaxies. Then these little small galaxies can merge to form bigger galaxies later on, and eventually they all merge to form clusters and those large-scale structures that you saw. So that's nice, because then you can go out and you can look at how clustering evolves over time, look at galaxies today, look at galaxies at redshift 1, look at how clustering is evolving, and you can convince yourself that observations show that the distribution of galaxies match that expected from cold dark matter. Okay, hence the cold dark matter paradigm. All right, so actually there's lots of sort of old school astronomers who like to think of galaxies that formed beginning of the universe and have just been sitting there forever. Okay, but if you come along with in the cold dark matter paradigm, we have a very different picture of small things forming first, coming together to form bigger things. I don't know if any of you have encountered the kind of debates that go between those groups. But it was very hotly debated because the observations initially it looked like galaxies were too similar out to redshift 1. There didn't seem to be that much happening to them out at least to redshift 1. And so in the sort of old version of cold dark matter, the cold dark matter people were predicting that you should see quite a lot of merging and things coming together from redshift 1 through to today. But that was a prediction that came from a universe that didn't have any of this kind of cosmological constants type stuff. Okay, so it's a prediction for a universe that is has a omega matter equal to 1. Okay, so if you start expanding the space at redshift 1 more and more and more, so that things can't fall together that much, as much. Okay, so you see less evolution in the galaxies out to redshift 1. So you find that the clustering evolution is consistent, like I showed you, with some cold dark matter and some of this lambda stuff as well.
Question?
Yeah.
Maybe you've already said this. I'd like to understand that there's actually some new, although albeit preliminary results, showing some surprisingly early galaxy formation.
Yes.
Is it too preliminary to really...
No, I think, are you maybe referring to the cosmic microwave background results, which show that the universe was reionized very early on? I think maybe, is that it? Well, there are a few things. One is that if you look at the cosmic microwave background, you see the effect on very small scales of the sort of... okay, let me step back a second. At cosmic microwave background times, we go from an ionized state to a neutral state, and then the universe becomes reionized again later on. And when that happens, tells you when the first stars turned on. And it seems to be it seems from the CMB results that the stars turned on early. Okay, and we also see some pretty big quasars early on, which need to have a big black hole, which had to have formed at some stage. So things are forming, but I understand it to be consistent with a lambda CDM model.
The worry is if they keep finding more of that, then it would be worrying, but right now it's still within.
I think that what happens is you can start, people look for quasars at very high redshifts, and you have a sort of volume of space where you find how many they are, and the numbers are consistent with what you would expect. And it's not like it could be that you're missing some at higher redshift in these surveys. So yes, that would be a problem. But it seems like they're picking out the quasars, and that is consistent with the structure formation.
What does the Z indicate in your picture?
That's the redshift. Okay, so today we're redshift 0. Okay, so we talked about that yesterday, where the redshift just gives how much the spectrum has been shifted, and so how much it's shifted is how fast it's moving away from the Doppler effect, and so that's it's a timing thing as well as a distance thing. Okay, so this is a CDM simulation. You can see it starts then at redshift 30, and you just get the gravitational collapse of dark matter forming structures which maybe you agree look a lot like those large-scale structures I showed earlier. Okay. Now, just looking at it obviously isn't going to be good enough, but you do some statistical analysis, and it's very convincing that these are the same sorts of structures that you see. Okay. So, where are we at? 1:45. Let me just show you something that, because these kinds of simulations, I did quite a bit of work on them, looking to see if you can really make the kinds of galaxies that you see in the universe within this kind of cold dark matter paradigm. Because like I said, it initially looked like observations were not all that consistent with this merging of galaxies picture. So you can try to, using sort of very unfundamental physics, to figure out how galaxies might form within these underlying dark matter structures. So here, for example, redshift 3, redshift 2, redshift 1, 0. So using sort of fairly simple ideas about how things would fall together within these dark matter structures, we can make up the galaxies that we see today, and it works pretty well. In clusters, it's still a bit difficult because there's lots of complicated things going on, so that's an area that lots of people like to look at. So these are just real galaxies from the Hubble Deep Field. And yeah, we've been running some simulations, like not exactly like this, because trying some slightly different ideas about the matter that's in the universe. So what I've got now is just some things, the kind of work that I've been doing. And I don't know if you'd rather that I could tell you results from, for example, the constraints on dark matter. Like I said, that you couldn't get, that not all the dark matter can be these little black holes, for example, in the halos of galaxies. So I can step through this. If you want to come up later and have a closer look at what this is about, here I'm saying that by looking at detailed observations of galaxies, you can find out something about the distribution of dark matter. And in fact, in these cold dark matter paradigm, within the cold dark matter models, there do seem to be some angular momentum problems. It is actually quite hard to make galaxies in detail, and particularly there are problems with the angular momentum. So there are 2 projects that we've been doing that involve that. Like I say, you can have a look later. Another thing that we were looking at was large-scale structure from this survey, the first survey. So this is faint images of the radio sky at 20 centimeters. It covers about an eighth of the sky, 700,000 sources. And the nice thing about a radio survey is you can probe these huge volumes of space. So like I said, when you're looking for the evolution of clustering over time, using these kind of radio sources can be a good thing to look at, because you do probe these large volumes. Okay, and we thought about doing some weak lensing on that. That's kind of ongoing, and looking at the clustering, and particularly a student was just looking at particularly the radio loud quasars, which we have. So you can probe large volumes, a large distance back in time. So that puts constraints on the clustering evolution, which, like I said, depends on the kind of contents in the universe. Okay, so I was just talking about the geometry. This is another kind of quasar sample where you can look at the geometry at around redshift 1. And, okay, so for traditionally dark energy, we have W equals -1 in the equation of state. I don't know if I should go into this. So, okay, but observations allow a range of negative W. Okay, so it doesn't have to be exactly that traditional cosmological constant type stuff. You could imagine sort of varying the equation of state a little, and so you get a slightly different geometry coming out, and that's something that you could look for using distances in quasar surveys. Okay. Yeah, just because we do these simulations, I work in a computational physics program, so it's nice to have lots of computational projects. We do those things like the visualization stuff that I showed you. And we're considering this crazy idea that maybe dark matter and dark energy are one thing with a weird equation of state. So just see if you can make a universe just by changing your ideas about the dark matter and dark energy. Okay, it's quite a long shot, but this is maybe is really exciting. The next generation CMB telescope from the WMAP team is a telescope that they're building in Chile. And you can get a lot of cosmological information from the interaction between the cosmic microwave background and the foregrounds. Okay? So they're building this telescope, and it needs optical follow-up of the foreground clusters of galaxies, and that's a perfect project for SALT. So me and these other 2 guys in Durban are going to do that part of that project, so that's really exciting. Obviously it's kind of a long-term thing, but that's really interesting. And I haven't talked at all about the early universe. Just remind you that as you go to higher and higher energies, that's where you start encountering all your grand unified theories that people have been talking about. I haven't talked about lots of other things. But let's stop there, I think. more down here as well, which I'll answer. Oh, okay. Is our galaxy a spiral one? Yes, it is. And if you know anything about galaxies, you'll know that, okay, so this is a spiral galaxy seen face on. If I look edge on in the plane of the board here, this will look like a flattened disk with a sort of bulge in the center. Okay, so the question is, do we live in one of these kinds of galaxies or a different kind of galaxy, which I didn't really talk about at all, but you get these other kinds of galaxies which are kind of just ellipsoidal like this, okay, like big rugby balls. We live in one that's quite like that, and if you know about the difference between a barred spiral and a spiral, our galaxy has probably quite a large bar in it, okay, which is kind of surprising. That's quite that's quite recent. Sort of in the last 10 years, people have come to realize that our galaxy is probably a barred spiral, not a spiral galaxy. Okay. Okay, so here's a question. Do we expect stuff in the galaxy just to flow towards the center? Okay. So I could just as well ask the question, is the Earth just going to fall towards the sun? And no, it doesn't, because it has a velocity and it's going around the sun. Okay? So that's exactly what happens. We've got velocities out here, so it doesn't just all fall towards the center.
What aspect of its velocity cancels over the force due to gravitational attraction?
Aspects of its velocity?
Well, I'm saying it has a velocity, but why does that stop it from falling into?
It's just... Isn't that obvious?
Just suggesting it might not be obvious to everyone who might want to talk.
Sorry?
That was a good tangential velocity. That, I mean...
Okay, all right, no, sorry.
Who knows the answer to that question?
Okay, sorry. I mean, okay, we have something traveling along here. It has a force inwards. Okay, so it travels a little bit, has a little force inwards. Travels a little bit, force inwards. Travels a little bit, force inwards. Do you want to correct me?
I can't remember the astrophysics, but what's called parking orbits.
Say again?
Something to do with what's called parking orbits.
Sorry, what sort of orbits?
Well, where you're
Parking
parking orbits, where when you get to the right velocity, like we do with satellites, it will just go around like that. It can't fall in.
Right.
I'm not sure. Yes, we got another question.
Yeah, that's it.
Okay.
Some weird question. Is it correct in our clusters, locally, galaxies and galaxies are moving towards each other?
Sorry, locally, are galaxies moving towards each other? Yes, that's, well, in a cluster, you have everything orbiting about the center of mass, okay? So, everything's on its own orbit in the cluster, okay? So, for example, yesterday we talked about the fact that the Andromeda galaxy is falling towards the Milky Way, yes.
Is it possible, since we can measure the velocities of the galaxies, we can actually measure the distance between the galaxies? If the motion is constantly safe, is it possible that one day we'll end up with a crash?
A crash with the Andromeda galaxy, yes. Absolutely. We would predict that in about 3 billion years we'll crash with the Andromeda galaxy. It's not all necessarily all that catastrophic, actually, because there's so much space between stars. Okay, if I make the sun this big, all right, and I look to see where the next star is, it's going to be 300 kilometers away. Okay, there's huge amount of space between the stars. So in some sense, the Andromeda Galaxy can just kind of move through us. But of course, we will sort of fall together because of the... Let's go into that, yes.
The galaxy is in rotation around itself. The galaxy.
Okay, so you're saying, does the sun go around the center of the galaxy?
No, all the galaxy. Galaxy itself is in rotation.
Oh, right, yes. So, to me, that's the same question as is the sun going around the galaxy, because the galaxy itself is stars, right? So if all the stars are moving around the center, then the whole galaxy is moving around. Okay? So, sorry. Then, yes, the sun is going around the center.
Are there any thoughts about dark energy being responsible for the expansion of the universe?
Are there any thoughts?
Yeah.
Yes, that's the major thought.
Is there any evidence, what kind of...
Sorry, I don't understand.
I think he's asking for a little different. You're asking about someone that be responsible for starting the expansion in the first place, or pushing it forward today? Today. Oh, yeah, I'm sorry.
Okay. Then today we think we see the universe, the expansion rate increasing with time, and yes, we attribute that to cosmological constant type stuff. Yes. Yes. Yeah.
The galaxies they can prepare this direction of rotation in space.
Do galaxies rotate?
Do they prepare direction like northwest and
No.
is it random?
Sorry?
Is it random?
Yes. Yeah.
If galaxies are moving away from us like faster than light speeds, how do we detect that?
Oh, let's go back to the diagram. Right. So we said that if you took a stellar spectrum, it would look like that. Galaxy is just a large collection of stellar spectra. Okay. So the galaxy spectrum is shifted somewhat if it's moving away. If the space is expanding such that it looks like the galaxy is moving in the faster than the speed of light, it's shifted a lot. That's it. How are we getting it when the space is expanding that fast? I think maybe you need to try and picture what the... yeah.
Another way of stating that question is, do we see galaxies that are receding from us faster than light?
Yes. So they have a redshift larger than 1. Okay, so the redshift is just the change in wavelength over wavelength. Okay. So if we have a magnesium line at 510 nanometers, and it's shifted by 500 nanometers. Okay, so here we have this line, and maybe now it's shifted down to somewhere near 1,000. Then the redshift is going to be, well, let me take that away, actually. That's confusing. Yes, yes. But what I was just trying to show was how it could look like that. Okay.
Wouldn't part of the explanation of that be once it's covered part of the distance, where the light is, some of the expansion of the universe is helping it get towards us, and some of it is. So, I'm not explaining this really clearly. As it moves along, there's not so much space between us and the light to cause it to expand away from us. So, the expansion of the universe doesn't.
However, expansion made it worse.
I don't know how to show this.
Yeah.
And how the light
is maybe what you need to picture is that earlier on things were smaller, and
So I also thought that the observable horizon is receding from us at the speed of light, so anything that's contained within it should be traveling less. You know what I mean?
yeah.
Informative or clarifying comments. So some of the equations I think that appeared relating redshift and velocity were actually for small velocities. And we made speed of light, there were some corrections in the The other thing is that it turns out we keep talking about a curved space-time at GR lecture that might come in sometime. There are various subtleties. But let me just mention that if you measure the velocity directly from the redshift, which is what astronomers do, then what you would mean by something, well, as the velocity approaches the speed of light in relativity, we know that the redshift goes to either 0 or infinity depending on my conventions. And which one is it? Must be 0. Okay. But in any case, so beyond the speed of light is something where the redshift goes beyond either 0 or infinity in that definition. And as you might guess, those are things that you cannot see. Okay? If the redshift is really bigger than 0 infinity, it is effectively, it's a cosmological version of being behind the black hole horizon. You will not see those stars.
Yeah, so we don't know.
You will never see.
We cannot get any information
You
about it.
cannot-
We don't know what galaxies. We don't know what galaxies are moving by since the light beam.
There's a very real sense in which no galaxy is moving faster than the speed of light. You shouldn't worry too much about it. But for those that are far enough away that they would have some kind of diverging vision, you will never see the effects of those galaxies.
Okay.
Any other questions?
I've got some more here.
Oh, they're more on the page.
Lots. Okay, well, maybe if you come up, why don't you stop it now and you can come up and ask me your questions. I can answer them here.